If we've got, say we have cobalt and sodium in our electrochemical cell, how can we tell which one is going to dissolve and which one is going to go to metal? We look at the nobility table, right? Which is not in this one. It's in 14. Will you need to write down this nobility table on your sheet? I will give it to you. Hope I remember to do that when I write the exam. Yeah, so we can tell which one is going to go to the metal by looking at the nobility table. So you see noble, cathodic, right? These want to be reduced because reduction always happens on the cathode. These want to be oxidized because oxidation always happens on the anode. And so if I give you a choice between which metal is going to be oxidized and which one is going to be reduced, all you need to do is look right here. Sodium's not on here because it's way down here. Sodium definitely likes to be oxidized, but cobalt is... Cobalt on here? No. Cobalt's not on here either. So I will give you the metals that are actually on this table if I ask you a problem like that. Yeah?
And can you also, like the book said, that the more positive the E values are, the more like cathodic is one?
Yeah, so the book talks about how this noble metal series relates to the table, right? And we didn't talk about that as much. I just wanted to give you a feel for noble metals versus non-noble metals. So this table will rule how we design problems. You won't have to go on which one has a more positive reduction potential.
But that does hold true.
Yeah, the book is true on that point, yeah, for sure. Yes?
That might be what he's trying to get at. So I was always taught, like, if you added two, like add an oxidation reduction to a reaction together, it should be positive and it's going to be thermodynamically favorable. So if you got a negative, the other reverse reaction was going to go.
Yeah, so that's a good point. We know that, well, we don't need to look it up. This, right? And so if delta G is positive, what do we know?
Yeah, negative, or delta is positive.
Then delta E is positive, and is that reaction thermodynamically favorable? No.
E is positive.
So if E is positive, or if E0 is positive, delta G is negative. So this one is thermodynamically favorable, right? And then the reverse. Yes?
Would that be delta G naught?
Yeah, I think so. Standard conditions here. Standard conditions here. So you should know if you have a positive E0 or if you have a negative E0, you should be able to tell me whether this is thermodynamically favorable or not. Yeah?
Well, we need to know Faraday's constant, or we'll leave that for
I'll just write it on your sheets. Yeah. Does anyone not know it by heart? 485. Yeah, I might give it to you if I remember. I'm not sure though. Faraday's constant?
Oh, Faraday's constant.
Yeah. 96, 485 coulombs per mole. Yes? Oh, no. Yeah.
What exactly is N in the equation?
Yeah. So what is N in this equation?
Number of electrons.
Number of electrons. Where do we get the number of electrons from? From the half reaction, right? Hold on. Let's see. What's the N in this set of equations? Why isn't it 4?
It's balanced already.
2 plus 2.
Same electrons?
It's the same electrons, right? The electrons that come off of the cobalt are the electrons that have to go into nickel. So the N only relates to one of the half reactions. Now, what if this wasn't balanced? What if we had a very strange species called nickel 1 plus? What's the n for, what's the n for this? 2, because we would have to balance it. What do we do when we put 2 in front of the reaction? What do we do to the standard potential? Nothing, right? We only change the n. And I gave you a homework problem about when the n changes to balance the reaction versus the standard potential. Remember, that cell potential didn't change. The n changed, and that changed the delta G. Yeah?
So I know a catalyst will lower the activation energy needed.
Mhm.
What does it do to the Gibbs free energy?
Yeah, what does the catalyst do to the Gibbs free energy?
Nothing.
Nothing.
Okay, so
Same reaction, right? We've never written any catalyst in there. We've never done anything like that. It only lowers the activation energy.
okay.
Yeah. So what would the slope, if we lowered the activation energy, if we have 2 lines on this plot, right? Which one is with the catalyst and which one is without the catalyst?
Oh, one with zone.
The steeper one is the one with the catalyst, right? The slope is higher. We know that this is negative EA over R. And so this slope right here will give us the higher activation energy. Doesn't change the delta G at all. And so we plot that like this, right? Reaction. Which line is with catalyst? Which line is without?
Bottom one is with catalyst.
Yeah, small activation energy. And delta G is the same. Questions?
So the top one is with the catalyst of the.
Oh, sorry, the bottom one is. Right? Higher slope will give us a larger value in the numerator, because this equals. Slope. Yeah.
Why do you want a larger activation energy when the catalyst is lower?
Oh, sorry. Catalyst equals smaller activation.
So which one's over the catalyst?
The one with the smaller slope. Smaller slope equals lower EA equals catalyst. I was thinking faster rate catalyst. Okay. Smaller slope, so smaller activation energy catalyst.
Okay.
Yeah.
What do we need to know about the concentration cells? I know it's like the 2 cells with porous membrane and the different molarities.
Yeah, so concentration cell, things you need to know.
Is that only like when the same elements used in both?
Yeah. So concentration cell is governed by a difference in concentration. So what equation tells us about that? Nernst equation. Okay, so E is E0 minus RT ln Q, right? I think that's the Nernst equation. Or you can put the 2.3 RT NF, sorry. Okay. If E is E0, what's Q?
Reaction quotient.
And if Q is 1, what do we know about the concentration of these species? They're the same, right? So if E equals E0, what's this term? 0, right? ln of Q is 0. Okay? If E equals 0, Q equals what?
KEQ.
KEQ. Okay? So under standard conditions, we calculate E0, right? So under standard conditions, what are the concentrations in those reduction tables that we see E0 at, right? So under standard conditions, if we're measuring E0, where is it now? Right here. Right? We have all these concentrations of stuff, right? We've got all these reactions, and we're measuring E0s.
At 1 mole.
Yeah, so it's at 1 molar, right? All things, if all the concentration of everything up here is 1 mole per liter, 1 over 1 to the whatever, 1 to the 6, 1 to the 10, over 1 to the 0, or 1 to the 2, always gives you a reaction quotient of 1. So that's how these E0s are defined. So at equilibrium, we have E is 0 here, right? So this log Q describes the concentration dependence of E on Q. So the most important thing you need to know about the concentration cells is that what's the E0 for a concentration cell?
0.
0, right? And so if we have equal concentrations here, if equal